Hello everyone, I hope all of you are doing well in your studies and enjoying your life. So today we are going to start our lecture number 6, Parallel Capacitors and Energy Stored in Capacitors, Grade 10, Chapter 6, Electrostatics. So we are going to study that what are the parallel capacitors and how the energy are being stored in capacitors. So let's begin our lecture. Parallel capacitors. What are parallel capacitors? You can see over here capacitors are always being attached with each other in parallel way. So parallel capacitors can be, you can say that if the two plates of a capacitor are parallel metal plates, it is called a parallel plate capacitor. And a parallel plate capacitor consists of two parallel plates, each of area A. So this parallel capacitor, each one have their own specific area separated by a distance d. So capacitor is charged, the two conductors carry equal but opposite charge. If the capacitors, both these metal plates are charged, we can say that both carries equal charge. Both carries equal charge, one carries positive charge, the another one carries negative charge. When the plates of a capacitor are connected to the terminals of a battery, means that when we connect this capacitor with the battery, the capacitor becomes charged. The plate connected to the positive terminal of the battery is charged to positive charge, and the plate connected to the negative terminal is charged to minus charge. Now here you can see we have to derive the relation for the parallel capacitors. And between this parallel capacitor, we know that there is dielectric medium or insulating medium. So we need to understand the relation and to understand the derivation, that how we are going to find the relation between this. So the capacitance of capacitor, this capacitance is directly proportional to the area of its plate. Now the capacitance, the ability to store the charge. Capacitance means the ability to store the charge. This is directly proportional to the area of the plate. If the area of the plate is larger, large amount of charge will store, and if the area of the plate is smaller, definitely small amount of charge will be stored in the capacitor. So here you can see the direct relation between the capacitance and the area. Capacitance is inversely proportional to the plate separation. If the distance between these two capacitors is larger, so definitely less amount of charge will get stored in the capacitor. And if the area is smaller, we can say that a large amount of charge will get stored in both these capacitors. So it have a direct inverse relation. Capacitance of the capacitor have a inverse relation with the distance between these two capacitors. So we combine these two relation and we put a constant value, because we need to convert this relation sign, direct relation sign, proportionality sign to equality sign. Now what is Ke? K epsilon naught. K epsilon naught is a constant value. So K is equal to epsilon over epsilon naught is a dimensionless dielectric constant. Dimensionless means which does not have any direction. So K is actually a non-directional dielectric constant. It does not depend on direction of the no conducting material, that is dielectric between the plates. So this K is actually the depends on the material of the plates. Depends on the material. Which material? This insulating material. So the K depends on the dielectric medium. So E is equal to 8.85 into 10 raised to power minus 12 coulomb square per Newton per meter square. So this is basically the constant value for K epsilon naught. K epsilon naught is equal to epsilon. For vacuum, K is always equal to 1. Now let's do some questions. Question number 1. A parallel plate capacitor has an area of 2 into 10 raised to power minus 4 meter square and a plate separation of 1 millimeter. Find its capacitance. Given value for this for this dielectric medium is 9 into 10 raised to power minus 12 coulomb square per Newton per meter square. So the given data is area. Area is given, that is 2 into 10 raised to power minus 4 meter square. And the distance between these two metal plate is 1 millimeter. That is 1 into 10 raised to power minus 3 meter. If we convert millimeter into meter, it will become 1 into 10 raised to power minus 3 meter. So we know that the capacitance of a capacitor having area and distance separation is this. So we know that for K, for dielectric medium is 1. Put the value in the equation, we get the final value to be 18 into 10 raised to power minus 3 Faraday, or 1.8 picofarad. Picofarad means 1.8 into 10 raised to power minus 12. Question number 2. A certain metal plate capacitor consists of two plates, each with area 200 centimeter square, separated by a 0.4 centimeter air gap. Part A, you need to compute its capacitance. Part B, if the capacitor is connected across a 500 volt source, find the charge on it and the value of electric field between the plates. If a liquid with the K is equal to 2.6 is poured between the plates so as to fill the air gap, how much additional charge will flow onto the capacitor from the 500 voltage source? So we need to see that what is the data given. Distance is 0.4 centimeter, that you need to convert this into meter, that is 4 into 10 raised to power minus 3 meter. And here it is minus 2 meter. And A is equal to 200 centimeter square. So you need to convert 200 into 10 raised to power minus 4 meter square. Yes, it is correct. 4 into 10 raised to power minus 3 meter, because it is 0.4. It is correct. So for parallel plate capacitor with air gap, you need to find the capacitance. We know that the capacitance between two plates is given. Putting the value in the equation, and after calculating, we get the capacitance to be 4 picofarad, or 4.4 into 10 raised to power minus 11 Faraday. And we know in part B you need to find the charge. Find the charge on it and the value of electric field. First you need to find the charge from the formula of capacitance. We know that Q is equal to product of capacitance and voltage. Capacitance we have found here, capacitance, and voltage is almost 500 volt. So we need to multiply both this value, and after multiplication we get the final value of the charge to be 22 nanocoulomb, or 22 into 10 to the power minus 12 coulomb. And we know that electric field strength is equal to voltage over distance. So voltage over distance, so voltage is given and distance between these two plates is 4.0 into 10 raised to power minus 3 meter. After doing the calculation, we get the final value of electric field strength to be 1.3 into 10 raised to power 4 volt per meter. So part C, we need to find the flow of charge. If a liquid with K value of 2.6 is poured between the plates so as to fill the air gap, how much additional charge will flow onto the capacitor from the 500 volt? So you need to find the charge if a liquid is added inside the dielectric medium. So we can simply multiply this 2.6 with the charge. We know that charge is equal to the product of capacitance and voltage. So here this 2.6, which is a constant multiplied by charge multiplied by voltage, we get the final value to be 57 nanocoulomb. And after that we deduct the final coulomb from the initial, from this value. After deduction we get the final value to be 37 or 35 nanocoulomb. Now energy stored in a capacitor. Suppose these are the two capacitors, and you need to store the energy. So when you charge a capacitor, use a power supply to push electrons onto one plate and off the other. So here you have to provide energy to push the electrons from one plate to another plate. So here force pushing electrons, other electrons on the plate repel this electron, and in doing so force pulling the electrons. So here the force is pulling these electrons. The force supply does work on the electrons, so their potential energy increases. You recover this energy when you discharge the capacitor. Is that clear? Whenever you are transferring charge from one plate to another plate, what happens? You are actually providing the force. So this force will compel the charge to cross this bridge. In order to charge a capacitor, work must be done to push electrons onto one plate and off the other. So you have to do the work, and this work is equal to the energy which is being utilized after discharging the capacitor. At first there is only a small amount of negative charge on the left hand plate. Adding more electrons is relatively easy because there is not much repulsion. So if you add more charge over here, repulsion will occur, and this repulsion will cause resistance in the flow of charge. As the charge on the plate increases, the repulsion between the electrons on the plate and the new electrons increases, and a greater amount of work must be done to increase the charge on the plate. So again, you have to do, the more you are providing the charge, the more you need to do the work. So here we can analyze through this graph. This is a graph, okay? So a graph between voltage supplied and charge being stored. And here you can see that the graph is a straight line graph. It shows the direct relation between voltage and charge. To how much level you are providing the voltage, to that much level charge is being stored in the capacitor. So this graph is very important. So this graph shows that the potential difference, that is V, increases as the amount of charge increases. It is a straight line because charge and voltage, they are direct related. Okay, so here you can see voltage and charge, they are direct related. First, consider the work done in moving the charge through a constant potential difference. This is given by work done. So we know that work done, we know that potential difference is equal to the work done in moving a charge from between 2 points. So work done is equal to the product of charge and potential difference. If we apply the same idea to the capacitor graph, in this graph, then the area under the graph is a right angle triangle. Then this area in the graph is actually a right angle triangle. And we know that the work done is equal to the, and we know that the area of the right angle triangle is equal to the 1/2 into base over height. And we know that the work done is equal to, work done is given by through these formula. Now we will discuss that how we derive these three equation for work done. Work is equal to 1/2 Q into volt. Why Q? Because Q here is the base. It is basically a right angle triangle. So work is equal to the area of this right angle triangle, and we know the area of right angle triangle is equal to 1/2 base, which is charge, multiplied by height, that is voltage. Okay, so this is the basic formula. From this basic formula we can also derive this equation and this equation. Now we will discuss how we are going to derive this. These three equations show the work done in charging up the capacitor. This is equal to the energy stored by the capacitor. This work done is equal to the energy stored by the capacitor. Whenever we are finding the work, it means that we are also calculating the energy of the capacitor, since this is the amount of energy released when the capacitor is discharged. Now we know that work is equal to 1/2 Q into voltage. So we know that capacitance is equal to the ratio of charge over voltage. From this equation we can derive the value of charge, which is equal to the product of capacitance and voltage. Now we will put the value of Q from this equation into equation 1. That is 1/2 in Q multiplied by voltage. So we know that Q is equal to CV. So this is the value of charge. We multiply these three variables, and after that we get the work done is equal to 1 over 2 multiplied by capacitance multiplied by square of voltage. So this is the work done. Keep in mind that this work done, this equation that we derive, this is actually the energy stored, the potential electrical energy stored inside the capacitor. So whenever we are going to calculate that how much energy is being utilized, we can also use this formula, because this work done is always equal to the output, and output is always equal to the energy. Work is input, okay? So here this is input formula. But whenever we are going to find the output, means that we are going to find the energy of the capacitor, we can also use this equation as well. So here you can also write E, energy is equal to 1 over 2 C multiplied by V square. Now here we can also derive, we know that 1 over 2 capacitance, so voltage is equal to ratio of charge over capacitance. Now we will put the value of V from equation 2 into equation 1, and after that we can say that the work done can also be equal to 1 over 2 multiplied by Q square over capacitance square. And this equation, again I repeat, that we can also use to find the energy of the capacitor. Let's do some questions. Question number 3. A 2000 microfarad capacitor is charged to a potential difference of 10 volt. Calculate the energy stored by the capacitor. So here you need to find the energy stored. Capacitance is given, that is 2000 microfarad, 2000 into 10 raised to power minus 6 farad, and voltage is, that is 10 volt. We need to find the work done, energy. We need to find the energy stored. But why work I mentioned here? Because we know that work is equal to 1 over 2 into C. Now this work, which is input for the capacitor, now this equation can also be used as the energy, because we know that work done is equal to the energy dissipated or energy utilized from the capacitor. So energy is equal to 1 over 2 multiplied by 2000 into 10 raised to the power minus 6 farad multiplied by 10 to the power of 2. After calculation, we get the energy to be 0.1 joule. Question number 4. A 1.2 microfarad capacitor is charged to 3.0 kilovolt. Compute the energy in the capacitor. So here we know that the capacitance is 1.2 microfarad, and we know that 1.2 microfarad is almost equal to 1.2 into 10 raised to the power minus 6, and volt is 3.0, that is 3000 volt. So the energy, we can also use the work formula for the energy as well. So energy is equal to 1 over 2 multiplied by 10 raised to the power multiplied by 1.2 into 10 raised to the power minus 6 into 3000. So after calculation, we get the final value of the energy to be 0.6 joule. Question number 5. A camera flash unit stores energy in a 180 microfarad capacitor at 300 volt. How much electrical energy can be stored? So you need to find the energy stored inside the capacitor. So here the capacitance value is given, that is 180 microfarad or 180 into 10 raised to the power minus 6 farad. Given voltage is 300. So you need to find the energy. We know that energy work is also equal to the energy. So energy is equal to 1 over 2 into capacitance multiplied by V square. Putting the value in the equation, and after doing the calculation, we get the final value of the energy is 8.1 joule. So this 8.1 joule of energy is being stored inside the camera flash. So I hope that you have understood the lesson. Do study, stay happy, and take care of yourself.